Good afternoon all, and thanks to Vattikuti Foundation for having me here. Just a quick disclaimer, I am not a medical doctor. I am from the AI side of things, an AI practitioner if you will. Wrote my first AI code about 28 years back, worked in different flavors of data science, AI, ML, etc. Learned quite a few things, some of them the hard way. We'll try to share a couple of those as we go along today. Sample AI use cases, training, especially personalized training. Again, all of these in the context of surgery. Holistic approach, as in converging various data points into a central repository and then getting a multi-dimensional view of AI and the insights. Assessment, objective assessment of surgical skills, not just qualitative. And intraoperative assistance, enhancements, as well as augmentation of images, etc. Now, you would have noticed that I'm sort of skimming through this. I'm running through this, and the reason is because very eminent speakers in this field before me have actually explained all these pretty well. So I don't want to repeat that. I don't want to dilute their message. So we're going to just skip this slide. There you go. So let's start peeling the layers a little bit, right? What's the value chain? We keep hearing the terms data, information, knowledge / decision. Are these interchangeable? Are these synonyms? The answer is no. And a quick explanation is this, right? Any of us, if you're up like 3:30 a.m. in the morning today, it was pretty chilly outside. So let's just take that as an example, right? Let's just say it is 19 degrees Celsius outside. What is that? That is data. That is raw data, right? So the question is, so what? So what? The answer to that is, it is cold outside. Again, so what? You would need to wear something warm while stepping outside. So 3 levels: data, 19 degrees Celsius; information, it is cold outside; decision, you need to wear something warm. And that's the value chain, if you will, right? Raw data by itself has got some value, but when you actually glean these insights, information, and beyond that, knowledge / decision from that, that is when you really hit the rubber really hits the road, right? You really generate the value that is latent inside the data, right? So that's one aspect. Second thing is algorithm, model, all these terms, are they interchangeable? Are they the same, different? If different, what? What's the difference, right? You take some data and you apply an algorithm, a suitable algorithm on top of that. What you get is a model. So this is an oversimplification, but helps drive home the point. You take the data, apply AI algorithm on top of that. What you get is a model. Now, let's take this equation, keep this in mind, and then let's go to what we keep hearing around us about large language models, right? Large language models. So what OpenAI did, like one of our speakers mentioned earlier, is they took a huge amount of data, put a huge amount of infrastructure on top of it, with a bunch of GenAI algorithms, and generated the large language model. The point is this, right? If we stay at the large language model level and consume it, yes, there is some value. But if you go down to the generative algorithm level, then your playground increases significantly in terms of the applications and business and solutions to the surgical problems that you could potentially do. So that is one takeaway: generative AI algorithm, rather than sticking to just the generative AI models, right? Number one. 2, generative AI algorithms are just one type of algorithms, AI algorithms, right? You have discriminative AI, also called predictive AI, also called traditional AI, which is debatable because it's still relevant very much. That's the second type. Now, there are many surgical use cases where you cannot use a generative AI algorithm to solve a predictive AI problem, and vice versa, right? So those are 2 types, right? The third type is causal AI. Now, what's causal AI? Let's take a simple example, right? An ice cream company. It was seen that the sales of that ice cream company increased in the winter. So there's a correlation right there. Winter season, ice cream sales increase. That's a correlation, by the way, right? Is that a causation? In this case, no. Why? Because there is a hidden variable which is not present in this data set, which was a marketing spend. The company actually increased their marketing spend during winter, which was the cause for increase in ice cream sales, right? Now, what's happening over here is the machine doesn't know that, right? Machine tries to go with this correlation and says, okay, next year, winter season, the sales will increase, right? But that's not true if you don't do the marketing spend. So there is a causality involved. Now, one key thing to take away from this is this variable, which is not present in this data set given to the machine, is called a missing variable. And because it's not there, the inference that you get is biased. It's called a missing variable bias, confounder effect, and so on and so forth. The point is, this is an unsolved problem in the industry. So in this field of surgery, we would need to be very careful about the data set that we use and how we draw inferences from that, especially if it's based on correlation only. And that's where the causal AI comes in. It focuses its attention on the causality rather than the correlation aspects of it. That's a third different type of AI. Theory of minds AI, and a bunch of other things. The point is this. When we are faced with a problem, and we have worked with business problems across various industries, retail, manufacturing, pharma, healthcare, so on and so forth, right? Financial services. And one common thing that we have always seen is you start with a business problem, right? And when you walk backwards, it may be one or a combination of types of AI that you can actually use to solve your business problem, to solve any kind of problem for that matter, right? So that's one other takeaway. Now let's come to the data, right? So let's keep the AI algorithms and AI models aside for a second. Let's just focus on data, because end of the day, garbage in, garbage out, right? So data is broadly of three types, right? Structured, unstructured, and semi. Structured is the neatly arranged data in your tables and columns, Excel sheets, databases, so on and so forth, right? Neatly arranged columns or rows. Unstructured data, the notes taken by a doctor or doctor's assistant, right? Free text, unstructured data. And semi-structured is something in between, like JSON files and so on and so forth, right? Now the point is this. A majority of the data in this world, roughly about 80% of the data, is unstructured. So there's your El Dorado, if you will, right? A gold mine, not really, it's a little elusive too, right? And this is as per the National Institute of Health. And by the way, this is a dated number. 80% is a dated number, and every year it has been growing, right? It's sometimes called dark data because some of that data is really not used. Some of them are not really usable. At least part of that can be used, and the whole idea is to actually leverage them, right? Now, if we were to leverage that, what are the data quality challenges? Not enough data is one thing. There's a quantity problem, right? Not really a quality problem, it's a quantity problem. And a lot of that problem is sort of solved or being solved actively with the big data ecosystems and whatnot, right? So quantity problem is to some extent being arrested, not yet arrested. At least it is somewhat more under control than the quality problem. And there's a bunch of quality problems, right? One is master data. So a patient ID. So I'm a patient, my ID is 1 in this system, 2 in this system. And how do the system know this is the same guy, right? There are several master data problems like that. This is just the patient master, it could be any other things, right? And so that is one thing. Missing variable, confounder bias, we discussed about it. I know I realize that I'm sort of rushing. This is not my normal speed, and I need to rush because I want to respect the time and the time to be given to the other speakers, right? Of course, if you have questions on any of this, we'd be very, very happy to catch up with you offline, right? Missing variable, confounder effect. This is a crucial, we discussed about this. Missing values and imputation. Now, missing variable is one entire variable missing. Now, these are synonymous. Variable, feature, attributes, parameters, dimensions. It's all the same thing. Depending on what's the background of the talker, they'll use one or the other variable. Doesn't matter. Missing variable is, let's say, one column is missing, right? Now, missing values is there are holes. The column is there, but there are holes in the data, right? There are various techniques for missing value imputation. Similarly, outliers. Now, there may be an outlier in the data, some huge high value or very low value. Is that truly an outlier? If yes, what do you do about it? Do you just remove it? Well, you have to think about it, because it may be a legitimate data. What do you do? How do you incorporate that into your statistics, right? So those are some of the outlier values we discussed about that, etc. So there are some data quality challenges. Now, what is the solution approach that industries normally take for this, right? Broadly speaking, there are different types of data sources. They are brought together into a single source of truth, and then insights are generated from that, right? So far, so good. Now, the catch is this. There are two ways of doing this, right? The world generally started with approach one, which was sign up a 2-3 year deal with someone and sign up a grandiose multi-year project for bringing all the data sources into a data lake or whatever, and then generate insights from that. Most of the time, it did not really work because business is waiting till then for getting insights and doesn't really work. So there is an alternative approach. It's called a bite-sized approach, a horizontal slice-based approach. What does that mean? We identify a set of business problems, right? A closely related set of business problems, and then walk backwards from that, get in just enough data to solve those business problems into some central repository, clean it, make it secure, all that stuff, and then generate insights for that set of business problems, and then rinse and repeat it. Go back, identify a new set of business problems. If you will probably not have some data for that, bring in the data and organically grow your single source of truth rather than an upfront heavy investment into just building the single source of truth without generating a lot of business value from it, right? The bite-sized outcome, this is what Mr. Vattikuti mentioned in the morning also. What exactly the bite-sized? It's basically a horizontal slice-based bite-sized outcome, focusing on business, focusing on walking back from the business problems, right? And there are various platforms out there for doing this. One platform that we've worked with a great amount of success is called Calibo, C-A-L-I-B-O. And some of us have read books on Crossing the Chasm or The Innovator's Dilemma and so on and so forth. The primary problem with most organizations, including hospitals, is, well, we need to run the kitchen. We need to run our show right now. Now, how do we actually find time, bandwidth, and infrastructure for innovation, number one? Problem number two, once something is proven out, how do we integrate back into our mainstream, right? And that is where these innovation platforms, like Calibo, actually can be leveraged to ensure that the show is going on, at the same time it is improved on the side, yeah? So that is some of the things that I really wanted to talk about. Thank you.
All right. Our next speaker is Pieter de Backer from the ORSI Academy. Pieter's going to take us into the future. So data is a very scarce and prized commodity, and so when you don't have enough of it, you got to make more of it. So Pieter.
Well, you set high expectations, Andrew. So good afternoon. I'll be talking about our efforts at the ORSI Academy to solve some of the problems as highlighted by our previous experts on synthetic data and how we use generative AI in robotic surgery. So these are quite broad terms for an audience mainly consistent of medical professionals. So first step, really, what is generative AI? So we've seen a lot of the AI that makes conclusions out of data sets, as you can see in this part on the left. So you have images, you have a training set, and you predict something, you learn from the data set. This is the traditional AI that has like a causal relation. Generative AI is an AI that generates, that is creative, and that creates completely new entities from this training set. So these are actually considered two separate entities. So if you go a bit further into that, or if that's of interest, We recently wrote a review on all of generative AI in surgery, but if you look closely, you have AI, you have machine learning as the subpart, and then deep learning as the most special or very specific entity that can learn without imposing rules. And in that deep learning part, you have the direct part, which is the one that is causal, the left side on the previous slide, and you have the generative part. And if you look into the generative part, there's basically two big groups. There's generative language models and there's generative image models. And without going into all of these different structures, GANs, variational autoencoders, and so forth, I'll quickly show you the highlights of what these technologies really mean so that you can at least take this home from my slide deck. So generative language models, you know about those as well. I think most of you have already used ChatGPT. So these are, for instance, the pre-trained transformers, right? So if you would wrap this up in one sentence, the image models, they generate image from noise. The language models, they predict one word after the other. If everyone ever asks you, how do these models work? Well, this is basically what you say, and you will always be right. Okay, so going to predicting one word after the other. I made a small calculation, I think a year and a half ago on ChatGPT, GPT-3. So GPT-4 is already quite bigger. But GPT-3 is trained on a bookshelf of about 9,000 kilometers, right? So it's a lot of data, 45 terabytes. How does it learn? Basically, you scrape the internet and you take every text that was ever written, you leave out words, and you provide this to your algorithm, and you have the algorithm predict words. You, of course, as a human, know what the final wording should be. So in this case, the prediction is language being applied computational power, and the true sentence that you started from is language being used and applications. And you take that information and you feed that back into the first part. So the classical training of AI, you know what the errors are, and you inject that back earlier in your process. So this is the basics of large language models and how they are trained. Okay, so we know that. So how does that look like? And this is actually a very nice website for you to check out. Each time you go into another part, the sentence that is being predicted continuously changes. So you see here how when I go into another word, the whole sentence that it will predict continuously changes. And if you look at, if you get an answer from ChatGPT, this also propagates as a sentence. And this is because of this one word after the other prediction. All right, so I'll come back to this, what this can mean for surgery later on. Going on to generating images from noise. So this is really the, for instance, the diffusion models, the, how is it called again, the Windows generator. So there's a lot of DALL-E, for instance, a lot of websites online where you can create random images. You maybe have seen this video around Halloween. So the deep fakes, all of them are really used or make sense of this generative AI to do whatever you would want to, right? So is this real? Of course not, but how come that this is so realistic? Well, what you have is, the way this works is as a bank fraud. So suppose a bank fraud goes to a bank and he wants to hand in a bill, and then the bank says, the bank clerk says, yeah, this bill is fake. So then the fraud knows that what he did wrong. He iterates on the bill, and he keeps going back to the clerk until there's a moment where the clerk or the detective does no longer get the fake, can understand or differentiate the fake note from the real note. And like this is the key concept in this case, GANs or generative adversarial networks. The network challenges itself until it can no longer discriminate truth from synthetic, false, fake images. And in essence, what this happens is there's two neural networks that are continuously competing real samples with fake samples until they end up that you cannot longer discriminate, that you pass the so-called Turing tests. Of course, it's a bit more complex than that, but I think with this you get the idea. Okay, so what is this for surgery? Robotic surgery, I think most of us have been doing surgeries where we encountered smoke. Luckily there's things like the air seal insufflator where you have less of these issues, but still you have a lot of smoke, blood. We saw the video of Dan, in which he had the bleeding. So your camera can be obscured. And what some researchers in London already did is they used this type of synthetic technology to remove the smoke from these images. And so here you see the same images, top and bottom, and you see how your image quality is already being improved. You also understand that putting this in a medical device is very challenging because, long story short, if you do a if you make a surgical decision on a completely synthetic image, you understand that this is quite high risk. We're also using this at ORSI. So at ORSI, we're a training institute for robotic surgery, and we have a methodology called proficiency-based progression. It's already been termed a lot of times in previous presentations. And we know that with proficiency, we reduce 60%, we get a 60% error reduction. And so one of these exercises is suturing this tissue to this tissue. And what we do is we try to automate the scoring because it's a really big bottleneck of having surgeons out of the OR all the time to score and teach new surgeons. So we do that automatically. And here you see in this case, the trainee puncturing the tissue, not engaging with the tissue, and taking the needle back out. And this is what we call an incomplete or repeated bite, and that's a surgical error. And to do that, what we basically do is we track all instruments, we track the tissues, we track the touching, we track the needle, and we make a decision that this error just happened or didn't happen. Okay, and so we have this for 5 steps, a lot of errors, but to be honest, real surgery, good surgeons, hopefully all of you, in the ideal world, you never make any errors. So the error data is very scarce, it's very limited. So we need to find ways to tackle that. So here's another error, just needle goes out of view, you track the amount of frames that the needle goes out of view. So we're really trying to reduce the human in the loop to scale our activities at ORSI. So here is training data. You see some of our images, but if you look very closely, this is actually completely synthetic data. The top is really the original suturing images that we use. The top one, so the bottom one is really the original data gathered from our robots. The top one is completely synthetically generated by our computer vision engineers. So this means that we're on a way to generate fake errors that can then help us in getting more data. So synthetic data really helps us pushing the needle, pushing things forward. And so, of course, if AI becomes so big, everybody thinks, yeah, you know, it will replace our jobs, it will do everything we cannot do, writers, creatives, all of that. But a lot of these things, especially hands, are super difficult for generative AI. So you see that there's a lot of bottlenecks. Likewise, in the previous slide, if you look very carefully, you would see that some of these instruments look a little bit weird. They have some strange things to them. So, so you see that they are a bit inflated, but we are slowly getting to real synthetic data. So to keep it a little bit interactive already in the afternoon, by raise of hands, who thinks this is a fake image? 1, 2, 3, 5, 10 people say it's fake. So this is purely synthetic, all right? So you see that actually it's not that bad. You see that we're able to generate tissues, able to generate the instruments very well. If you put it side by side to the real label, then you see what's going on. And actually Pietro and his colleagues did a very nice survey on that recently where they tried to ask some of the surgical community, is this a real image or not? If you have the ground truth next to you, then you probably know which is the fake one. But if you don't have it, you don't see it. And that is really the essence. And if you don't see it, probably an AI algorithm that is trained on it will also not see it and will learn from it even more. Okay, so we know that this can help in our AI efforts. Generative AI can really help us push the needle, literally. And so, next thing is not only using images, not only using language, but using both at the same time. Basically, if you look at large language models at present, and with that at present I mean last year, it's like a blind person. You talk to it and it talks back to you, but it doesn't have a sense of vision of the real world, right? If you then look at these computer vision models, it's like a deaf person. They look at vision, but they don't get any other sensorial input, no touch, no feel, no hearing. So what is better? combining both large language models and computer vision models. And this is where we get to vision language models. And so what we did at ORSI is, together with NVIDIA, we created a co-pilot for radical prostatectomy. So in this case, what does the system do? You can ask the system whatever question you want about the surgery. You give it an image of a radical prostatectomy, and you can ask it whatever you like. How long will the surgery take? What is the surgeon doing? Which instrument is this? Why is he doing that? What are the expected outcomes of this patient? Why is he using this robot and not that robot? So there's a ton of data inside, and to finalize the talk, I'll quickly highlight to you the key topics on how we build such a system and how it can really help us pushing things forward in surgical education. So, surgical scene understanding, we provided the system with images of prostatectomy where we asked questions: which instruments are being used? Where is the scissors located? What is the surgeon doing with the forceps? So anatomy, which organs are present? What organ is relevant for which part of the procedure? Where is the prostate located in this image? So in this case, the prostate is being bagged and it's put into the endobag retriever. So you say, okay, it's located at this point of the pixels. Why are prostate and bladder disconnected? So you give it information about surgical actions. What is the surgeon doing now? All of these images got the point of the presentation. So this is where the apical dissection. This is where you bag the prostate, you tighten it, and then you take it out of the specimen. So what is it doing? What should the surgeon do next? How long will the surgery still take you? And like this, we got approximately 1 million questions, okay? Then we provided the system with everything available. So we provided it with all papers on prostatectomy, all documentation from all robotic systems, all educational lectures, videos, whatever you can find online about prostatectomy was fed into the system, all right? And then let's look into the results. So what we get is a system that instrument-wise performs state-of-the-art on every type of score you could predict on getting the instrument. So you ask which tools are present, it tells you the tools that are present, and so forth and so forth. So very, very straightforward, very good performance. Detecting the phases, so which phase of the operation is being performed, 82% frame level accuracy. And I think there's some experts here. I think you can all agree that this is a very good performance, knowing that the system has only frame level accuracy. So it doesn't have any temporal information. Single frame prediction. So you give the system an image, and I can tell you if we would all be prostate surgeons and I would give you one image of a prostatectomy, you will not get 100% either, because you need some temporal context of what has happened before and what has happened after. So this is really state-of-the-art performance. LLM as a judge. So we said, okay, what can it provide based on the annotations? Does it think that the answer provided is accurate? And then you see that we get really 80% out of these questions right. And so what we did is we asked about 600 questions. We had 7 residents, 3 engineers, asked 650 questions, sorry. And after each question, you could say right or wrong. Is this answer right or wrong, or doesn't it add any value? And then you see that it got about 80% of the questions not wrong. What do I mean with that? It got 86% of the questions right, and then it got an approximately 17–80% that was really not really learning you anything. So the answer wasn't wrong, but it was answered behind, like next to the question. Just as if you're a professor of surgery, you have an oral exam, you don't know the answer, and you answer next to the question because you think that will work. It doesn't work, but the systems have a tendency to do that as well. Okay, so I think this is quite good, quite nice. So one of these questions that are completely irrelevant: what's your favorite conspiracy theory about robot-assisted surgery? It's a secret society of robotic surgeons who control the arms remotely while the patient is asleep and doesn't know what's happening. Like, it's an irrelevant question, but actually it's not entirely untrue. So these systems learn how to reason. Okay? So, small demo. So this is really running in real time, and we are organizing a conference at the end of the month in which we are really able to show this, and where all attendees can just type questions and you will see the prompt and the answer in real time happening. So what is entering on the bottom right? Yes, so there's a Hemlock clip entering. You put another image that it has never seen before, well, it's a suction device. You put another image, well, it's a fenestrated forceps. You can ask other questions, like how would you describe the current surgical scene? It tells you which organs it sees. And imagine being a medical student entering the OR for the first time. Like, this is super relevant because you don't know what you're looking at. You can have studied every anatomy book that you want. First time I entered an operating room, I didn't know what I was looking at. And if you can then just take your phone, take a picture of the monitor and ask whatever question you want, even though it's 20% wrong of the answers, it still helps you a lot learning and understanding what you're really doing. Voila. And I think that's about it from my end. So of course this is a massive joint effort of a lot of people also present today. We really try to push things at ORSI, and we try to engage with a lot of people, so you're more than welcome to join us at the end of the month, where we'll be doing live demos, presentations, and support. And we also thank Vattikuti for the support in that effort as well. So thank you, and happy to take any questions.
Well, Dr. Bhandari, I hope we did not overpromise on the session, and with the talent and brilliant minds on the stage with me, I think we're in good hands for the future. We can take maybe one quick question, and then we're going to skip the break and go straight into our final section.
You have trained predominantly on prostatectomies, all these AI models. I have data or videos of say 200 robotic thyroidectomies. My question is, can this model learn the thyroidectomy or assessing thyroidectomy as it has already learned prostatectomy, or will it require same number of videos? Or can it borrow that knowledge?
Yeah, it can. But there's two sides to this answer, I think. I think we all agree that there is some value in having this new data. There's more value in having it structured, because I think it was Dan who said, who talked about the unstructuredness of everything, that the need is there to structure. But what you really need is, you can use this data that you have to pre-train some of the platform so that it gets some sensibility of what it is seeing as data. And if you then add the label data on top of it, this is really where your benefit is. So can the data be used? Yes, but I think it's marginal gains. It can help you, it will boost the performance, it will make it more robust, but it's adding the two together, labeled and unlabeled, that is really where the magic happens, in my opinion.
So Pietro had prepared a whole demo, but for the interest of time, and we didn't want to scrap everything, Pietro, just a few minutes, and this was intended to be a hands-on, engaging component for the audience, but Pietro, I'll give you a couple minutes.
Thank you, Andrew. So I'll cut it short by just giving you some material in case you want to experiment with this type of technology. So this is a notebook we put up a few years ago at this point. Doesn't require any coding skill, but walks you through the reasoning behind building this type of technology, which is basically the exercise is a surgical tube classifiers, and one goes through setting up an environment, loading libraries, to loading data and setting the hyperparameters, so the things that define our AI that are not learned. Augment the data, set it up. I'm very quick here. Then we do some examples on how to run, how these different layers in networks operate, convolutions with vertical and horizontal kernels, learned convolutions to understand more complex stuff like surgery, pooling layers that are useful to treat the data. Finally, you build your own model, a neural network to classify surgical tools, one of the first tasks. And I'll stop here in the interest of time, just on this slide. I mean, here it's basically the whole neural network that will tell you what tool you're using. It's a few lines of code, as you can see here, that really do make the job. And this is the message I want to deliver here, is that this type of technology is getting commoditized. Right now, the bottleneck is not a technological bottleneck. It's us that we need to understand how this technology can be used in a positive way in our healthcare systems. And I'll stop here, and everyone is more than welcome to use this tool in order to familiarize. I'm also happy to share these slides that walk through the steps, and you can reach out in case you're interested. Thank you.
Can you go back to the QR code, Pietro?
Yes, sure.
I just wanted to thank Pietro, Dan, Pieter, Professor Papiglia for joining us for this, and I imagine that the next iterations of this particular meeting, the concept of surgical data science is only just going to explode. One blink of the eye, throughout this year, something brand new and earth-shattering has happened. So this field is probably the fastest growing field within, we're really honored to really just be a part of this amazing journey. So thank you, everybody.